Hello everyone, I am Ayman Shabir, a PhD student at Aalborg University in the Energy Department's Advanced Biofuel Group. Today I will be presenting my first year research on the aqueous management of PET hydrolysis. This research focuses on depolymerizing PET by recirculating the aqueous phase. I'll start by explaining the hypothetical NHTP reaction of PET. PET is a polymer composed of terephthalate and ethylene groups. When water attacks the ester bonds of PET under NHTP conditions, it breaks down into terephthalic acid and ethylene glycol. By weight, PET consists of 77% TPA and 23% EG. In terms of carbon distribution, TPA contains 80% of the carbon while EG contains 20% of the carbon. In reality, when we conduct the reaction in our lab under NHTP conditions at 250, 280, and 310 degrees Celsius, the carbon for PET gets distributed into solid and aqueous products. About 80% of the carbon ends up in the solids, while 20% is in the aqueous phase. Of the carbon in solid phase, 30 to 60% is in the form of TPA, with the remainder being TPA moieties and degradation products. Similarly, in the aqueous phase, 30 to 40% of the carbon is in the form of EG, with the rest being EG moieties and degradation products. This brings us to the idea of aqueous phase recirculation. Water is the largest fraction in the reaction. Can we save it? If so, we could significantly reduce the water footprint. How can we achieve this? In the aqueous phase of the product section, we mainly have water, around 98%, with the rest being EG and its moieties. If we use this aqueous phase to depolymerize PET and obtain monomers and repolymerizable esters, we can recover the carbon ending up in the aqueous phase by continuously accumulating it there. This approach not only conserves water but also enhances the carbon recovery. Let's explore the potential of the aqueous phase. Since the aqueous phase is mainly water, we can expect the hydrolysis reaction to occur. With about 1.2% Eg present, glycolysis might also take place. Additionally, the presence of acids, esters, and alcohol in minute fraction contributes to the synergistic acidic effect, lowering the pH to 3.2. This acidic nature can catalyze the hydrolysis process as well. The question we aim to answer are: will we see better depolymerization, more esterification, or increased degradation? Understanding these effects will help us optimize the process for improved efficiency. To investigate this, we designed batch experiments. We start by reacting PET and water under subcritical NHTP conditions. The resulting product is a mixture of solids and aqueous phase, which we separate by centrifugation and filtration. We then analyze both phases using NMR. In the solids, we find TPA, esters, and degradation products. In the aqueous phase, we detect EG, aldehydes, acids, esters, and water. We use this aqueous phase for recirculation to depolymerize PET, creating an aqueous phase mixture with 67% AP and 33% water. This process is repeated for up to 4 cycles at 3 different temperature conditions. For cycle 0, we use a 1 to 10 weight ratio of PET to water, and for cycle 1 to 3, we use 1 to 10 weight ratio of PET to aqueous phase mixture. The process uses 20 ml stainless steel microtubular batch reactors. For quantification of compounds, process uses NMR method developed by IBSOR. We have a complete experimental setup in our lab for these experiments, including a sand bath, microbatch reactors, assemblies for monitoring temperature and pressure, and equipment for product mixture and separation. For the analytical quantitative NMR, we utilize our chemistry lab facilities. The setup allows us to thoroughly investigate the aqueous phase recirculation and its effects on PET depolymerization. To present my work, I will show you how we interpret the results by defining compounds based on the number of TPA and EG units they contain. For instance, in solids, we have TPA with the chemical formula as seen on the screen. which we assign 1 TPA unit and 0 EG unit. In the aqueous phase, we have EG with the chemical formula as seen, which we assign 1 EG unit and 0 TPA units. Let's consider an example in solids. We have BH, which based on its chemical formula has 1 TPA units and 2 EG units. Similarly, in the aqueous phase, DEG has 2 EG units but no TPA units. By analyzing these units, we can better understand the distribution of TPA and EG in our products. We also analyze the results by categorizing compounds as either desired or degraded. Desired compounds can be repolymerized into PET, while degraded compounds cannot. In the aqueous phase, we identified 5 different compounds, with the remainder being degradation products. In the solid phase, we found 8 desired compounds, with the rest being degradation products. This classification helps us understand the efficiency of the process and the potential for recycling the compounds back into PET. Here I present my results in the form of TPA-EG units at 250, 280 and 310 degrees Celsius for NHTP at 20 minutes. On the left hand side, the stacked bar chart shows the yield of TPA units, and on the right side, the stacked bar chart shows the distribution of EG units under 3 different NHTP conditions separated over 4 cycles. We observe that in all cases, the depolymerization of PET into TPA and EG monomers remains relatively constant across the cycles. Similarly, the depolymerization into EG and TPA units is also fairly consistent in each cycle. Lastly, the extent of degradation remains constant, varying only with the temperature conditions. Let's examine these results in terms of carbon distribution, focusing on 310 degrees Celsius NHTP case. In the first cycle, we observe that approximately 80% of the carbon from PET ends up in the solids, while 20% is found in the aqueous phase. Of the 80% carbon in the solids, about 60% is in the form of TPA, with the remainder being TPA moieties and degradation products. For 20% carbon that ends up in the aqueous phase, 30 to 40% is in the form of EG, with the rest being degradation products. In the fourth cycle, as you can see, we are using AP mixture here. The carbon distribution between solids and aqueous phase remains consistent with earlier cycle. We observe that approximately 80% of the carbon from PET ends up in solids and 20% is found in the aqueous phase. Of the 80% carbon in the solid phase, TPA varies between 60 to 62%, while of the 20% of the carbon in the aqueous phase, EG varies from 35 to 40% in the aqueous phase. This indicates that the PET depolymerizes to consistent TPA recovery in the solid phase, while EG also remains stable in the aqueous phase. The carbon distribution table shows that out of 80% carbon in the solids and 20% carbons in the aqueous phase, 79% is in the form of desired product in solids and 18% is in form of the desired product in aqueous phase. Overall, this means 97% of the carbon is in the form of the desired product, with the remainder being degradation product and the undepolymerized PET. We wanted to figure out whether hydrolysis, glycolysis, or the acidity of the aqueous phase is driving the depolymerization of PET. So we designed 2 different set of experiments. For the role of EG in the aqueous phase, we used mixtures of water with 5% and 30% EG and depolymerized PET under the same conditions. To test the acidity, we made solution with TPA and water, and the other one with IPA and water, measuring their pH and then running the reactions. These results helped us finding out what was actually causing the depolymerization. So as you can see on the left hand side, we have yield of TPA units and yield of EG units for different reaction conditions. One for neutral hydrothermal processing at 310-20. The second one is for EG 5% reactions and EG 30% reactions. Based on these results, it's clear that at higher EG concentration, glycolysis is favored. While at lower concentration, hydrolysis predominates. Given that our aqueous phase contained less than 5%, e.g., hydrolysis is the primary reaction in this case. This aligns with our observations and helps clarify the mechanism driving the depolymerization period. On the right hand side, the stacked bar chart shows the yield of TPA and EG under different acidic conditions compared to neutral hydrothermal processing conditions at 3 and 20. Our results indicate that acidity doesn't affect the yields or the chemistry of the process, suggesting it primarily facilitates the hydrolysis process. So after all this, I will conclude my research on these 5 points. First one is aqueous phase recirculation helps in depolymerization of PET. Chemistry of the process is not affected by the aqueous phase recirculation. Hydrolysis dominates due to over 90% of water present in the aqueous phase. Reduction in water footprint up to 67 with these batch experiment design, we found out. And future work will focus on optimizing aqueous phase recirculation conditions for efficient PET/PET based depolymerization by hydrothermal processing in a continuous setup. So after this, I thank you all for this opportunity, providing me this opportunity to present our research work with you guys. This is our research group, and once again, thanks a lot.